Folks, tonight we're doing a definite integral that involves the ceiling function. Now, the ceiling function always returns an integer, and so most of the work for this problem is just going to be arithmetic. Taking the definite integral of an integer is almost trivial. Now, let's just look at a concrete example here. What if we did the ceiling of, let's say, 6.7? Okay, now you're looking for the smallest integer that is greater than 6.7, okay? So in this particular case, that would be equal to 7 itself, right? Okay, and that's since 7 minus 1. Again, we need something formal like this to work this problem. Is less than 6.8, 6.7, excuse me, less than or equal to 7, right? Again, you can just read off the answer that the ceiling of this is 7, just because you know that's the smallest integer that's greater than 6.7. But we need a formal definition. So let's get busy on this problem. Now, one thing that's quite important here actually is to notice the nature of this integrand without the ceiling operator. This is something that can be shown very easily just by sketching a graph of this basic rational function. This would look like you would have a vertical asymptote at -8. We'll call this -8 over here, -8. All right, and then, because again, that would make this thing, there would be a divide by 0, and then you get this very precipitous behavior near what they call a vertical asymptote when you're dividing by 0, okay? And then, so the graph of the function ends up looking, and also you have what they call a horizontal asymptote at y equals 10. Okay, that happens when you take the limit as x gets large. So the graph gets closer and closer to this thing called the horizontal asymptote. And the graph looks something like this, okay? And this is a totally legitimate way to determine if a graph's increasing. This is very basic stuff that you learn in college algebra, graphing rational functions. And the rest of it's up here if you need to know. But we just need to know that this thing is increasing to the right of -8. In fact, just to the right of 0 for our purposes, okay? So anyway, once we get that out of the way, we can actually talk about what's going on with this function for values of x greater than 0, okay? And notice that I considered the two intervals 0 to 1 and 1 to 2. The reason why I did that, it's fairly simple. If you need to know when the signaling is going to change, so you look at when you're switching from one integer, at one interval at an integer level to another integer level interval, if you want to call it that. Where we got this 5/9 is we just set 10x plus 3 equal to 1. And again, I won't go through all that. It's just a little bit of work, but it's not much trouble. But I set it equal to 1 because we have to have some idea if we need to split the integral. If the entire integrand was trapped between two integers for the entire limits of integration, you wouldn't have to do this, but that's not the case here. But anyway, when you solve this, you get x is equal to 5/9. Okay? Now for that reason, and again, maybe what I just said made 0 sense, but this was based on the nature of the limits of the integration, you see. The limits of integration of the original problem is from 1/3 to 11/12, right? And so we have to check to see what this rational function is doing in this, between these limits of integration, okay? And so that's why I did what I did right here. I set it equal to 1, we get x is equal to 5/9. And it's not hard to establish that the rational function is trapped between 0 and 1 if x is between 1/3 and 5/9. And notice that the fact that we know that this rational function is increasing is very useful right now. That's why I did this piece right up here. The rational function increasing on this interval, anything to the right of -8, is actually quite important here, okay? Now, what is that? What does this imply right here, folks? Well, we got this rational function trapped between 0 and 1. That means anywhere on this interval 1/3 to 5/9, the floor function or the ceiling function is just going to take on a value of 1. Okay? Again, folks, it's if x is x between these two numbers implies that the radical, not counting the ceiling function, is between 0 and 1. It's very easy to prove. It's very straightforward. I'm just writing it down factually here. Okay, so this is equal to 1, and in a similar fashion, to the right of 5/9, this guy is between 1 and 2. Okay, so the ceiling would be equal to 2 right here. Okay. Again, I could have shown a little more detail, but hopefully the main work is just setting it equal to 1 and noticing that at 5/9 it's where it's switching from the bounds, these integer bounds of 0 and 1 here, to the integer bounds 1 and 2 here. And that affects the ceiling, the evaluation of the ceiling. So what do we get right here, folks? Well, that you know very well that the definite integral of a constant is very easy to calculate. All you have to do is, this is going to be the height of the rectangle. This 5/9 minus 1/3 is going to be the width of the rectangle, and the interpretation is area here. So what we have right here, folks, is 5/9, which is a bigger number than 1/3. 5/9 minus 1/3. Okay. Times 1, and I'll just go ahead and emphatically put a dot here and a 1. Okay. All right, plus, now our new limits of integration, we had to split it. This is just the area property of the integral. Okay, you have 11/12 minus 5/9. Okay. And then again, let me put a dot 2 here. And y'all, literally, y'all, this is the area of a rectangle of width 5/9 minus 1/3, height of 1. This is the area of a rectangle with 11/12 minus 5/9 times 2, which is the value of the ceiling in this interval, just like 1 is the value of the ceiling in this interval. Okay? So what does that end up being? Well, you got me, let's see here, 5/9 minus 3/9 is 2/9. So this would be 2/9 right here, right? Okay, now plus, okay, what in the world's this? Well, the 36 is going to be your least common denominator here, right? So you would have, let's see, 3 times 12 is 36, so you'd have 33 minus 20. I'm getting 13 over 36, folks. Again, I'll double check myself here. 13 over 36 times 2. Again, let me double check here. So 3 times 12 is 36. That means there's a 33 in this numerator. 4 times 9 is 36. That means there's a 20. So 33 minus 20 is 13. And so this would be 2/9 plus, what is this, 13/18? Okay. And y'all, this would be 4/18, so I'll just write 17/18. 17 over 18. And I don't think I made any mistakes with the arithmetic there. Maybe you guys can verify. But anyway, the main idea of what we're doing is more important than any arithmetic blunder. So anyway, that's the solution, folks. And again, I hope I showed enough detail. Sometimes I say too much, but I hope what's going on right here makes a lot of sense. It's essentially based on the fact that you know that this graph is increasing anywhere to the right of -8. And also we need to find out where these bounds change. And they change exactly when 10x plus 3 over x plus 8 is equal to 1, right? And I didn't tell that out, but I double check this. You do get x is equal to 5/9 here. And that determines how we split up our integral. We change the limits of integration accordingly, okay? And then again, no need to even find an antiderivative. This is the standard area sum of rectangles interpretation of a definite integral. So y'all, that's it. 17/18 is the answer. Hope you liked it.